When we talk about technology, we tend to focus on all the amazing things it can do. We can message somebody from the other side of the world. We can visit amazing virtual worlds. We can video call somebody who is thousands of miles away from us. And now with AI, we can write, create images, and even brainstorm new ideas. But for all of that advanced technology, there are some things that are still missing. You can talk to somebody from the other side of the world, but you're not going to be able to shake their hand. You can visit amazing virtual worlds, but you will not be able to touch anything in them. And you can interact with all sorts of incredible machines and robots, but chances are it is going to be a bit awkward. So technology is very advanced, but it is also in many ways removed from what it means to be a human being. And one of the places where that shows up the most is the sense of touch. I work in robotics and haptics, which is the science of touch, and it really has two souls. On one hand, you can model and understand how we use the sense of touch to understand the world around us. On the other hand, you can use that technology to augment human beings. Now, the reason why the sense of touch is important is that we do not experience the world as disembodied brains. We move around with our bodies. We understand the environment and objects around us through the sense of touch. And we routinely do things like feeling the warmth of a cup before we take a sip, feeling the sensation of softness from cotton or fabric, and feeling the sensation of touching somebody else's hand. But when it comes to modern technology, very often it is very much removed from all of this. Robotics and AI are advancing so quickly. Every year, everything is more sophisticated, more autonomous, more optimized. But then it is really optimized just for what it can do and not for how we interact with it. And I had an experience of this a few years ago when I was working on upper limb prosthetics. So there are really two main ways to control an artificial hand. One of them is myoelectric control, where you use electrical signals from the muscles to control the hand. And the other one is called body power control. And in this case, you just have a cable that is attached to your shoulder, and then you physically pull on the prosthetic hand to open and close it. And often in this case, you have a very simple hook that can open and close. And it turns out that even when people have access to the more advanced myoelectric technology, often they still prefer using a body power hook. And the reason for that is that they feel more in control. They're better able to understand what their prosthesis is doing just because of that physical connection through the cable attached on their shoulder. So this is an example of a technology that is on paper very advanced, and it looks like it will work better than the old technology, but then when you deploy it in the real world, it kind of flops. And it sort of fails because it is missing the mark with the user. And at the end of the day, people just don't like it. I lead a research lab called the Human-Centered Haptics and Robotics Lab, and we are trying to build systems that think about the user from early on. Let me show you what I mean with just two examples from the work that we've been doing. The first example is about equine therapy. So about 2 years ago, people from our local Salt Lake City VA came to me with a very interesting problem. They see a lot of people with PTSD, and for a lot of people with PTSD, traditional therapy works very well, but for about half of the people that they see, it just does not work. So they're trying to figure out if it is possible to use some alternative approaches, and one of them is equine therapy. And in equine therapy, you go and interact with a horse, and there is something about the experience of interacting with such a majestic animal that can be very meaningful for people. However, there are some challenges with accessibility, and it is especially difficult to have access to this if you are somebody with a physical disability. So they came to me, and they wanted me to build a system where you can do equine therapy in virtual reality, so that you could give access to all sorts of people. But of course, the challenge is that to do equine therapy, you kind of need to pet a horse. And right now, you cannot do that in VR. So we needed to add some kind of touch component to it. Now, we could have built some kind of really complicated animatronic horse, but they didn't want anything like that, right? They wanted something simple, ideally low cost, and small enough that you could transport it to a hospital room, but still give people that sensation of reaching out to touch a horse. So with those requirements in mind, it became clear very quickly that it would not have been possible to build something that would feel exactly the same as a real horse. However, what we thought we could do is try to understand the main elements of the touch experience that you have when you go and interact with a horse and build them in a simplified representation of that experience. So the first step is understanding what are those simplified elements, and in order to do that, we did what any reasonable person would do, which is we went to pet a real horse. And two things immediately were noticeable. So the first one is that a horse is a really big animal. When you pet it, it kind of feels like a wall. You touch it, it's an immovable object. The other element was that the horse felt differently depending on where you were interacting with it. So the face is really, really soft, almost feels like a kitten. The body is a lot more coarse, and the mane is somewhere in between. So that gave us some elements that we could use to build a simplified representation of that experience. So we went back to the lab and we built it. So to render the sensation of the horse as an immovable object, we relied on vision. So when you are in VR, you have a visual representation of your hand, and your physical hand is moving in space. Normally, the visual representation of the hand tracks your real hand, but when you touch the horse, the virtual hand stops on the surface of the horse. And it turns out that even if you can physically push past that with your real hand, because there is nothing physically stopping you, the fact that you're seeing your virtual hand stopping is enough to give you the sensation of touching a solid object. And then for what concerns the sensation of different sensations when you're touching different parts of the horse, we use the glove that you see at the bottom of this figure, where you have a bunch of small vibrotactile motors. So by playing with the actuation of those, we were able to render different vibrations with different intensities and different patterns, and we made sure that when you touch the face, the body, or the mane, they all feel different, okay? So once we built this system, the next step was to evaluate it and try to understand if it's a meaningful experience. So to do that, we did a user study, which is a pretty standard thing that we do in haptics. The first thing was introducing participants to the system. We trained them, and then we had them experience the equine therapy in virtual reality with the system that we built. And we asked them a few questions. We tried to identify their emotional state through some surveys. We asked them how realistic the experience felt. And we evaluated other metrics of user experience. And we did this after different conditions. So we have different variations of the haptic feedback that we were providing. And then we had a control condition where the glove was turned off so that we could do a head-to-head comparison. And we also looked at how good they were at discriminating between different parts of the horse. So that is what we use the setup that you see over here for. We have these blank spheres. Each sphere has a specific sensation attached to it. You go and you pet it in the virtual reality environment, and then you select which area of the horse it was supposed to represent. And I'm going to show you just some highlights of the results for the sake of time. But over here on this plot, you see that we have 4 boxes. And the first 3 are just the 3 different types of haptic feedback that we were giving them. And then at the very end, you have the control condition where no haptic feedback was provided. And you see that in terms of accuracy of identifying which part of the horse they were touching, they were doing very well when haptic feedback was provided. Haptic feedback also made the experience feel more realistic, and overall it led people to liking the experience more. And then finally, and perhaps most importantly for our intended application, it made their emotional state better. So over here you see a result of a survey where we evaluated their emotional experience, and at the bottom you have a very sad face, at the top you have a happy face, and we asked people to essentially select the corresponding icon that represented their emotional state. And you can see that with haptic feedback, on average, we push them a little bit higher towards the happy face. So this is an example of an experience that is very much simplified. Petting a horse does not feel like your hand buzzing slightly. But even if it is simplified, it can still be meaningful. But that leads us to another interesting problem. So if you can build an experience that is simplified but still meaningful, then how do you know which parts of the touch experience you need to identify to deliver that meaning? And how do you do that when we're all different and we all have different opinions on what is meaningful and what is not meaningful? This is a very difficult thing to do. We are very good in haptics at understanding the effect of haptic feedback on how well you're doing in a certain task. We are a lot worse at understanding how it shapes your emotions and how it shapes your user experience in general. So for the second and last project that I'm going to talk about today, we had this very difficult question, which is, how do I build a touch experience that people will actually enjoy interacting with? And how do I do this in a way that is going to be tailored to specific people that are interacting with the system? And at first glance, this seems almost impossible to do because we're all so different from each other. We all like different things. But it turns out that we're less different from each other than one might think. So this is my wife. She used to work at a pet store. And after a few years working there, she came to the conclusion that when people see a chameleon for the first time, they react in one of a small handful of ways. And yes, one of them is singing Karma Chameleon out loud, which turns out not as original as one might think. So what that means is that when we experience something, we all have different reactions, but there is not an infinite number of reactions that you can have. And if that is true, we might just be able to model that process. So to do that, we build the system that you see over here. The core component is a knob. When you turn the knob, you move a cursor on screen up and down, and then there is a target that is also moving up and down, and the goal is to move the cursor so that it overlaps with the target. And then we change a few things about this system. We play with the level of resistance that was being offered by the knob. We play with how difficult the task was, so how fast the target was moving on screen. And we showed the score to some people, and after that, we also had a condition where the score was not being shown. And then we tried to evaluate the overall user experience. So we did measure their performance, which was quantified by a score that was determined by how good they were at staying close to the line. We evaluated their emotional state in the same way that we did for the prior project, and then we kept track of which configurations of the experience they preferred. And I'm going to show you the results. So this is a busy figure, but there are just two important things to understand about it. So first of all, this is a table, and as a table, it has rows and columns. And the rows that you can see with those horizontal bands are connected to the parameters of the experience. So they represent the effect of each of the parameters, in this case on score, because we're evaluating performance. And there are also columns which are a bit more difficult to see I will explain why in a second, but the columns represent that effect on each individual participant. And then you have the last column all the way to the right that represents the overall average effect across everybody. Now, the reason why the columns are difficult to see here is that you see we have these horizontal bands, so the colors represent a specific effect, and the effect was the same for all participants. So there was no variation in how each specific parameter affected their performance, their score, across participants. So you see that the overall average effect is also the same as what you have for individual participants. But it was a very different story when you look at the results for emotions and preference. So this is the same figure for preference. You see that it is an absolute mess of all different colors. And what that means is that you could give the exact same configuration to different people, and they would have very different reactions to it. And this is important because people will not use a system just because it does well in some performance metric. You're going to use a system if it fits your life, if you like it, if you want to interact with it. You're not going to use a system if it feels frustrating, awkward, or you just don't like it. And now if you look at the very last column to the right, so that is the population effect for the preference, you see that it does not match the colors of the individual models. So that is not a good way to model the individual reactions of each participant. And in fact, it is not a good way to model what is happening at all. So you can use population models to model performance in a task, how well you're doing in a task, and that is going to work okay, but you can't really use that to understand how people feel and what people prefer when they interact with the system. So these are just two examples of the work that we've been doing in our lab to try and build systems that can help people, and we try to do so in a way that doesn't just focus on evaluating how well people do in a certain task, but we also want to understand how it makes people feel. And this is important in general, but it is especially important in some applications like rehabilitation, assistance robotics, mental health, and social robots, where the technology is only going to work if people keep interacting with it. So the long-term plan cannot just be to build more and better technology. We need to start thinking a bit more about building more human technology that is simple, robust, and can adapt to what people actually want. If robotics, AI, and technology are going to serve people, they cannot just be built on efficiency, speed, and capability. They also have to be designed about with some thought put into what it is like to live and interact with these systems as a human being. The best technology in the world is completely useless if it doesn't serve the needs of the people that it was designed for. And I think that there is a real opportunity to build systems that don't just do more, but are also better at working with us. And this can start with something as simple and as overlooked as touch. Thank you.